Welcome to Empowered Learning. This video will be about solving second-order linear, homogeneous, ordinary differential equations where the coefficients for those equations are constants. In particular, what we are going to discuss in this video is the three different forms of a general solution for these types of ordinary differential equations. We're also going to explore why those three general solutions come up as they are, and then we're going to do several examples. So the first thing I want to make sure that we understand is, what do we mean when we say a second order linear homogeneous equation with all constant coefficients? So in general, this is what the equation looks like. So here, notice that our first term will be some real number times the second derivative of a function plus another real number times the first derivative of some function plus another real number times the actual function. And of course, what makes it homogeneous is that it equals 0. Now notice that this function y here usually will be either a function of x or maybe a function of t. This is what we are actually trying to solve for. So of course, in differential equations, we have equations where the solutions to those equations are actually functions instead of just numbers. So our goal here is to find out what is our y of x or y of t going to look like. And when we study this specific type of differential equation, it turns out that the general solutions that we come up with are relatively easy to get, but there's a lot of foundational work that we have to do to support us being able to skip a lot of steps. So part of this video is going to be going through the process of showing you how we derive these general solutions. If that's not really your interest, you can go ahead and speed forward in this video to get to the point where I actually start doing the examples. I would say you need to stop at least at the part of the video where you see that I do a summary of all three cases. Again, I'm going to go through it from the beginning and just kind of say, hey, this is a general solution to this differential equation. Depending upon some conditions, we can get three different forms of that general solution. And then after that, I'm going to go through the summary and then, of course, do examples. All right, so to start off with here, the main thing that we want to get across is that for the type of equation that we just got through looking at, a general solution for it is the function e raised to the rx, where r could be a real number or a complex number. So what that means here is that I can have something that looks like e raised to the 2x, or I can have something that looks like e raised to the 2 plus 3i. X. I can have that. Okay. No matter if I have real number here for R or complex number here for R, these types of functions are general solutions for a second order linear homogeneous ordinary differential equation. Now, the process that I'm going to take you through is showing you how, if we were to use just a general form here. So basically, if we use e raised to the rx and we were to find its first and second derivatives, plug it into a general second order linear homogeneous ODE, you will see that that function will satisfy. However, you're also going to see that it will satisfy it given some kind of conditions. And so those conditions will end up being basically the different ways in which we can, the different ways that solutions could look for the quadratic formula. Okay. And then, of course, based upon whether you're going to have a double root or two distinct roots or going to have complex roots, your solutions are going to look different. And so in general, that is what we're about to go through. Okay. All right. So let's move forward. So first, we see that we want to verify that this particular function is a solution to this type of second order differential equation. And of course, you see that I've stated the original function, taking its first and second derivatives. And then, of course, in place of y double prime, put the second derivative in place of y prime, first derivative, and in place of y, the original function. And then, of course, from there, we notice that we have a e raised to the rx that is in common with all three terms. So we factor that out. And what we end up having left here is essentially a quadratic expression. Now, because the fact that any exponential number that's multiplied times a positive constant, so here I have an understood 1, we know that the graph of those functions can never touch or cross the x-axis, which means that they will never equal 0 at any time. So here I can divide both sides by e raised to the rx and be confident that this side is just going to be 0. So as a result of that, we see that what we essentially have here is a quadratic equation. And of course, we could solve a quadratic equation by using the quadratic formula. And thus, what R ends up being, or what it ends up looking like, depends upon, of course, what our A, our B, and our C will be for this quadratic equation. And so now what we're going to do is go into the three different cases of quadratic formulas and see how does that translate to general solutions for these types of equations. So for the quadratic formula, basically the formula that we use to solve quadratic equations, we know that we can tell the type of solution we'll get based on the discriminant. And of course, the discriminant is just this b squared minus 4ac, which is essentially the expression under the square root sign, or the radicand expression. The three different types of solutions we'll get is based upon whether the radicand is positive, the radicand is 0, or if the radicand is negative. And if you remember from college algebra or basic algebra 2, if you took that in high school, is that if our discriminant is positive, then we're going to have two real distinct numbers for a solution. So we'll have something like a 2 and a negative 1/3, something like that. When our discriminant equals 0, then of course we have a double root. So an example of that would be, let's say if I have x plus 2 quantity squared is equal to 0, then my solution to this is going to be x equals minus 2. But because I have a 2 in the exponent here, meaning the multiplicity of this particular factor is 2, then technically what that means is that this 0 shows up twice, okay? But it's the same thing. And of course, in the last case, when our discriminant is negative, we have complex conjugate solutions. So we would have something like 2 minus 3i as a solution for one of them, and let's see here, 2 plus 3i for the other. So those are examples of what that might look like. So now what we are going to do is go through each of these scenarios here, and we'll call this case 1, case 2, case 3, and see what do our general solutions actually look like. So for case 1 is the easiest case, and since we have two real distinct numbers as a solution or as a root to that quadratic equation, ar squared plus br plus c equals 0. Since we have two real distinct solutions, then of course we can just use the fact that e raised to the r1x and e raised to the r2x are both solutions. And because of what we learned about the superposition of fundamental solutions for the basis of solutions for these types of differential equations, we can do any linear combination of these two and come up with the general solution. And so that is our case 1. Now for our case 2, that's going to be a little bit more involved. And that's mainly because of the fact that even though we're going to have two zeros, they won't be distinct, meaning that both of the solutions that we have based upon the quadratic equation here are going to be the same thing. So remember how I said we had this situation here whenever we solve this equation, where the solution to that is -2, but since I have a multiplicity of 2 here, it's going to show up twice, okay? Now, in terms of what that does for us in having a general solution for this type of differential equation, it doesn't really help us out a whole lot, okay? So what we know is that e raised to the r1x is the same as e raised to the r2x, so we have one distinct solution. Okay. Now, if you've been following my videos, one of the things I hope popped up in your mind is that if we're trying to find two distinct solutions to complete our basis for a second order equation, a differential equation, and we already know one solution, we could use the process of reduction of order to find the other solution. Okay. And that's exactly what we're going to do here. So we are essentially going to say if one solution is e raised to the r1x, then we're going to say that by reduction of order, we're going to assume that our second solution would be another function of x times what y1 is. Okay. And then if you remember from the whole reduction of order process, we would have to take the first and second derivatives of this function here, plug it back into our ODE, and whenever we work everything out, we know that all terms with our function u of the lowest order, meaning in this case all terms that just have u in it, they should be able to cancel out with all the other terms so that we essentially have no terms of u in our equation. And then from there, we could possibly do some more substitution to bring down the order of our resulting equation by 1 so that we can solve it using first order linear methods or first order equation solving methods, or something else a little bit more direct, like directly integrable. Okay. So we're going to go through that process here quickly. So here we see that if this is original function, then our first derivative will be this, and our second derivative will be this. And again, I'm not trying to go through all the gory process here because that's not the focus. The focus here is just to kind of show you how we actually get these general solution forms and then use it. The main thing that I'm trying to do here is to show you how reduction of order is used as a tool to help us to get to where we want to get to. Okay. So once we have the first and second derivative of what we propose our new solution to look like, then we substitute it into our original ODE here. And of course, everything you see here is y double prime, everything you see here is y prime, and everything you see here is y. From there, this next step is just showing you that since every term that I had an e raised to the r1x in it, I factored that out of each term here separately, and then out of all of them all together. Okay. And just like we said before, this quantity can never be 0, so I could always divide both sides by it and not do any harm. And this would be the result when I end up with that. And so notice here that we have our real number constant a here. We also have a real number constant that will be represented by 2a times the value of the quadratic equation solution that we got whenever we initially solved for the solution to that a r squared plus br plus c equals 0 back at the beginning. Okay, have the same thing here. Now, when we look at this at first glance, it looks like we're kind of stuck. But the great thing here is that we know that if I was to take my value of R1 that I got from the solution of the quadratic equation, I know by definition of that, if I plugged in R1 into an expression like this, it would go to 0. So that means this expression here would go to 0. And that's exactly what I'm trying to state down here. Okay. So notice that all these terms here have a u in it. So essentially all this is just going to go to 0. And what I'm going to have are these two terms left on the left side of this equation. Okay. So once we know that, then we note that, hey, this last major term here is going to be 0. And we have just these two terms left. Okay. Now, it also turns out that whenever we have b squared minus 4ac is equal to 0, our result from our quadratic equation here is going to be negative b over 2a, as a result. And of course, we know that because the quadratic formula is minus b plus or minus square root of b squared minus 4ac, all that over 2a. And if b squared minus 4ac is equal to 0, then all of that is 0, and all you have left is this. So we note that. And if I was to take this and actually substitute it in for what r sub 1 would be, I would get what you're seeing here. And notice that by me substituting in a negative b divided by 2a, right here for R1, I also end up getting 0. Okay, so that's great because now what I essentially have here is that this is 0 and all I have is a times the second derivative of u is equal to 0. And if we get to that point, we essentially have u double prime is equal to 0, which is directly integrable. And that's very easy to deal with. I just take the general antiderivative twice. So here, if I take the antiderivative of the second derivative, I get the first derivative. And since the second derivative was 0, then that means the first derivative has to be a constant. And of course, if we do it one more time, the antiderivative of a constant function is a linear one. Okay. And so just like how we did when we studied reduction of order in the reduction of order videos that I recorded, we see here that we ignore this K1 and this K2 because all we're really concerned about is the root function there, which in this case is just X. And so we don't worry about these constants here because if we kept them, we would still end up having, for a general solution, it'll just be rolled up in there. So there's really no point in carrying it with us. All right, so because of that, we know that u is equal to x. So that means that y sub 2, which is our second solution that will complete the basis or the fundamental set of solutions for our second order linear homogeneous equation, will just be x times e raised to the r1x. So because of that, we now have two functions that are both solutions to our second order linear homogeneous equation, and thus we could write out our general solution for equations of that ilk as just being the linear combination of those two functions. And I express it either explicitly this way or just with the e raised to the r1x factored out. Either way is fine. All right, so for the third case, and all I'm stating here is that since we know this, we will never go through the whole process of reduction of order. There's no need to actually have to do that in practice when you do these problems. We just want you to know that based upon the solution to the quadratic equation, if the solution ends up being a negative b over 2a, or put another way, if your discriminant is 0, then you automatically know that this is going to be the form of the general solution. You just need to know what R1 is and fill in everything else. Okay. All right. So for case 3, remember this is the case when the discriminant is negative. And by definition, if our discriminant is negative here, then that means square root of a negative number is technically a imaginary number, or we can just say in general, a complex number. So that means that this particular solution will take on this form here, okay? And all I did to get this form is just to rewrite b squared minus 4ac as a minus 4ac minus b squared here, okay? And then, of course, this could be rewritten as square root of negative 1 times square root of 4ac minus b squared. And by definition, we know that square root of negative 1 is I. So that's why you see the I right there. So from that point, we know that what we have here is the imaginary part of our complex solutions. And here is going to be the real part. So I rename it as lambda plus or minus omega, or you can just say wi. And just make sure I make that note. And of course, in this case, the 4ac minus b squared is positive. So that's actually going to end up being a real number inside of here now. Okay. Now, in general, what this means is that our general solution looks like this. So it's going to look like e raised to the complex number here times x. And of course, I have a plus or minus, so it can be either or. And so using exponential rules, I can rewrite it. This is the real part. This is the complex part or imaginary part. Okay. Now, we know that for this portion here that has the I in the exponent, if we recall Euler's formula or Euler's relation, we know that e raised to the I theta is going to be cosine theta plus I times sine theta. And of course, e raised to the minus, that the only thing that changes now is that we have minus here. So these two are essentially conjugates of each other. Okay. Now, if we were to actually just say, well, in general, what is that solution going to look like, then I could just say that y1 is just going to be e raised to the lambda x times all that. That'll be one solution. And of course, the second solution would be the same thing, just use the conjugate. Okay. And of course, in this case, since cosine is even, cosine of negative omega x will just be cosine omega x, and sine of minus omega x is going to be negative sine omega x. So that's why it'll look like this. The good thing about what we have here is that we do have a general solution. The bad thing about what we have here is that everything is still in complex form. And so one of the main reasons why the second order linear homogeneous equations, where the coefficients are all constants, is very important to us, is because it's used in a lot of applications. Okay. And in these applications, the applications are modeling things in real numbers. Okay. So to have something that needs to be modeled in real numbers and I end up trying to model it in complex numbers is not helping me out too much. So although these are actually solutions, to be able to model something that's going to deal with only real numbers, those solutions aren't helpful to me. Now, luckily, one of the things that we can do is we could use the fact that any linear combination of the fundamental basis of solutions is also a solution to a differential equation. So what that means here is that if I was to add my result for y1 and y2 together, this would also be a solution to the same differential equation. Okay. If I was to subtract these two, it would also be a solution. Okay. If I did 2 times one of these solutions minus 2 of the other, this would also be a solution. So the choice I have to make here is to figure out what linear combination do I need to come up with that's going to allow me to end up with a general solution that only deals with real numbers, okay? Well, it turns out that if we were to add these two complex solutions together and then take the difference of these two and then multiply it by I, we would get exactly what we're looking for here. And so I'm going to go ahead and show you what that looks like next. So here, if we add the two complex solutions that we had here, you'll see that when we add, we have the I sine of omega x and minus I sine of omega x. And of course, all that times to e raised to the lambda x. Those two terms will cancel each other out, okay? And I just kept the e raised to the lambda x on the outside just to make life simple. So that's why you see these two terms canceling out here. And of course, what we end up getting is just a function that's in terms of cosine, okay? And of course, here, our constant here is just going to be 2, okay? And so it could really be anything, but in this case, we want to keep it as general as possible. So I name this one y sub 1 bar is e raised to the lambda x times c1 times cosine of omega x, okay? Now, if we do the other suggestion, which is take the difference of these two functions and then multiply it times I, then of course, after some math, we see that we end up getting just same kind of thing, but now it's just in terms of sign. And again, the general constant here in this specific case is going to be a -1. But again, we want to keep it as general as possible. So here we see that if I was to add this y sub 1 bar and y sub 2 bar together, what I would essentially get here is going to be a linear combination of e raised to the lambda x times cosine of omega x and e raised to the lambda x times sine of omega x. And of course, here I don't see any terms with I in it, so I know that I'm going to be dealing with all real number valued situations here, okay? And this is what we need. So this is a solution out of many solutions for that case 3 form of our second order linear homogeneous equation, but it's the one that works for us as far as being able to model real valued things, okay? So now that we've seen how we get these general solutions here, the next thing that we are going to do is go over a summary of all these and then go over several examples so that you get used to seeing these. All right, so here for the summary, again, we remind you that in general, e raised to the rx is a general solution to this type of differential equation. What constitutes what our r is going to be will be this quadratic equation here, and we will refer to this equation as either the auxiliary equation or the characteristic equation. All right, so now let's go through the 3 cases here. So of course, case 1 again means that when we solve our quadratic equation here, our characteristic or auxiliary equation, the result ends up being 2 distinct real numbers. We know that because our discriminant here is positive, then we just write constant e raised to the first number times x plus second constant e raised to the second number x here, okay? So all this stays the same, constant here, you can just call it C1, C2, A, B, whatever. But the only thing that really changes here are these numbers here, okay? Now for case 2, when our discriminant is 0, we solve our quadratic formula. we know that we're only going to get one solution. And of course, whatever number that is, we can just plug it into this general solution formula here. So whatever R ends up being, because we've already done all the heavy lifting of doing reduction of order, we already know what the final form looks like. We just plug it in. Then lastly, whenever we have case 3 situation, meaning our discriminant is negative, we know that we're going to get complex conjugate solutions. They are going to be of this form. And of course, we could write our general solution in either this way, or you can go ahead and distribute the e raised to the lambda x's in. Doesn't matter. And so for this type of differential equation, that's really all you need to know. Okay, if you can just remember these 3 different cases here, it's pretty straightforward in solving these types of equations. And so we're going to do several examples to actually show you how straightforward it is. So for the next set of examples that I'm going to have here, these are all going to be case 1 situations. And so I'm doing several different examples of case 1 situations, just so that we can see, well, how do we deal with our characteristic or auxiliary equation, depending upon the types of numbers that we'll get. Okay. So we see for this particular differential equation, pretty straightforward. All of the coefficients are constants. It follows the format of the second order linear. It's homogeneous because equals 0. So we know automatically from that this is a second order linear homogeneous equation. We put together our characteristic equation. And of course, this comes from here, where our A is just 3, our B is 7, and our C is -6. So really all you have to do is know what this number, that number, and that number is going to be, plug it into your characteristic equation here, and then just solve that quadratic equation. And of course, for this one, we can just do simple factoring. I know we talked about the quadratic formula, but notice that we want to take the easiest route possible to solve these. So if you can factor out the quadratic expression in your quadratic equation, do that. If you want to use a quadratic formula or completing the square, you can do that. The thing is that you just need to solve it so you can get the values R so that you can put those into your general solution. In this case, this is factorable, very easy. So we see here we set each of these factors equal to 0, and we get that 2/3 and -3 will be the roots of this characteristic equation here, or this characteristic equation here. And all we do is just plug those values into our general solution, and we're done. Okay. And for most of these, unless we have some initial conditions, that's pretty much all there is to it. Okay. All right, so let's see the next example. Next example, the same thing. Here, characteristic equation is just going to be r squared plus 3r equals 0. And here, again, we know that because this is our A here, understood 1. This is our B. And of course, we have like a 0y here. So A is 1, B is 3, C is 0. And again, we just plug in. And for this one, again, it's easy factoring. Once we do that, we see that 0 and -3 are the roots. So we just plug this in, 0 here, -3 there. And of course, anything raised to the 0 here is going to be 1. So we just have C1 plus C2 e raised to the -3x as our general solution. Okay, so for this next example, it's very similar to the example that we just did before. Of course, we have some initial conditions for this one as well. We see here that since we have both the y double prime and the y prime terms, that lets us know that we have the first 2 terms of our characteristic equation here. So remember, characteristic equation is going to be this. So this goes with the y double prime term. This goes with the y prime term. So that's why our characteristic equation here is just r squared minus 9r, where of course the understood 1 here is our a, and the minus 9 here is our b. And since we don't have a term with y in it here, that's why c is assumed to be 0. So with that, of course, we factor out the greatest common factor of r, and we see that either r is equal to 0 or r minus 9 is equal to 0, which means that r is equal to either 0 or 9. So our general solution, since this is two distinct real numbers here, we just plug in the c1 e raised to the r1x plus c2 raised to the r2x. r1 is 0, r2 is 9. Here's our general solution. And so from there, if we apply the first initial condition, we see that wherever we see x, let it be 0. And of course, let y of x itself be equal to 1. So when we do all of that, plug in 0 here into the second term. And of course, e raised to the 0 times anything is just e raised to the 0, which is 1. And ultimately, this means that c1 plus c2 is equal to 1. So here, c1 is equal to 1 minus c2. Okay? Now, if we take the derivative of y of x, then of course you see here we end up just getting 9 times c2 times e raised to the 9x, and we let x equal 0 and let y prime of x equal 0. So of course that's kind of easy to figure out what c2 is going to be in that case. Ends up just being 0 once we work everything out. Thus c2 is 0 and c1 is just going to be 1 minus c2, which ends up just being 1. So if we go back up to here, all this goes away and all we have left is this. So what we end up actually having is a constant solution. Okay. And so we see here that y equals 1 is actually our constant solution there. Okay. Now, in saying this, one of the things I want to illuminate here is that it is not unusual for us to have constant solutions to these types of differential equations. In this instance, it just so happens to be a constant solution that is non-zero. And if you look at our initial conditions, you'll see that y of x equals 1 actually meets the conditions of our initial conditions. So if we go back up here, remember that y of x equals 1 is just a horizontal line. And of course, we have the point 0, 1 on this line. And of course, the instantaneous rate of change or slope of the tangent line will be 0 because, of course, the slope of any horizontal line is 0. Okay, so it makes sense that our solution of y of x equals 1 would actually satisfy this equation and these initial conditions. Now, with that being said, I also want to remind you that for these types of equations here, we will always have a constant solution of y equals 0. Okay, and so I say that because if I go ahead and write out this equation here in general again, if y is equal to 0, then that means that the first derivative is equal to 0, which means that the second derivative is also equal to 0. And of course, if I plug that all into y prime, and y double prime, I'm just going to have 0 equals 0. So we call that the trivial solution just because we know it always happens. We can always expect it. In the grand scheme of things, it is not something that we necessarily worry about because we do so much work trying to get the other non-constant solutions that are not 0. But it is good to know that for these types of equations, y equals 0 for all values of x will actually satisfy it. So if you are taking a differential equations course and you have an instructor or professor that wants you to always state your constant solutions, it is a good thing to state those. Okay, I don't do it here just because it is a trivial solution, but it is a solution. So to be on the safe side, you might want to write that out whenever you solve these types of equations. Okay, safe to do it that way. All right, so we'll go ahead and work this one out together. So we see here we have a second order linear homogeneous equation. So right away, what we can do is just go straight into our characteristic equation. We need to point out what A, B, and C are. So here, our A is 1, our B is -8, and our C is 15. So what that means is our characteristic equation is going to be r squared minus 8r plus 15 is equal to 0. And it turns out that this one is easy to factor. So we just have r minus 5 times r minus 3 equals 0. And of course, if we set both of these factors equal to 0, we will get r is equal to 5 and 3 respectively. Okay. So what that means for us is that r1, we'll let that be 3, r2, we'll let that be 5. And it doesn't matter if you let r1 be 5 and let r2 be 3. That part really doesn't matter. Okay. So our general solution here will be y of x is going to be c1 e raised to the r1, which is just 3x, plus c2 e raised to the r2, which is 5x. All right, so I had to clean that up a bit to make it look a little better. So now we have our general solution. Important, but because we have these initial conditions here, we're going to have to find what C1 and C2 are. So to do that, we are going to need the first derivative because of this initial condition. So I'm going to go ahead and find that out now. So from knowing the general solution, we're going to get the first derivative of the general solution. Of course, our constants we ignore. The derivative of e raised to the 3x is just 3 times e raised to the 3x. And we'll do something similar here for the second term. And this is e raised to the 5x and times 5. And of course, if we kind of write that in the way that we would normally write it, it will end up looking like this. And so now that we have our original function, that is a solution to this differential equation and its corresponding first derivative, we can use these initial conditions. So our initial condition of y of 0 is equal to 5. So here, y of 0 equals to 5 is basically going to be 5, which is going to be this side of it, equals c1 e raised to the 3 times 0 plus c2 e raised to the 5 times 0. And of course, e raised to the 0 times anything is just going to be e raised to the 0, which is 1. So this is 1, that's 1. So we see here that 5 is equal to C1 plus C2. Okay. All right, so if we use the second initial condition, and this is y1 prime of 0, and that's equal to 19. Then here this means that 19 is equal to, so here 19 is equal to, and so this will be 3c1 e raised to the 0 plus 5c2 e raised to the 0. And of course, the e raised to the whatever times 0 is just going to be 1. So this is 19 is equal to 3c1 plus 5c2. Okay. And so now at this point, we have two equations, two unknowns. We could solve for C1 and C2. And I'm going to elect to do this by using the elimination method. So I'm going to rewrite these here. And what I'm going to do is multiply both sides of this top equation here by a -3. And what I'll be doing here is essentially trying to eliminate the C1 variable. So if I do that, that'll be -15 minus 3C1, minus 3C2. And this will be 19 is equal to 3C1 plus 5C2. And I don't know why I had just a 2 there, but all right. So from here, if we add, of course, we know that this term will cancel. -15 plus 19 is 4, and minus 3C2 plus 5C2 is 2C2. And if we divide both sides by 2, we see that C2 ends up being 2. So if C2 is 2, this implies that from here, this is 2. Then this tells you that C1 is 3 because 2 plus 3 is 5. So here are our specific values. And so now our particular solution which will be our unique solution for this case since we have an initial value problem, is going to be y of x is equal to 3e raised to the 3x plus 2. That's what that should be. 2e raised to the 5x. And let me make sure I got that all right. Yep. And so this would be our final answer to this differential equation here. All right, so I have one more case 1 example, and I've thrown this one in here just because the initial conditions look a little different than normal. Notice that our initial conditions here, I have this irrational number e being used. And so because of that, that makes this look a little different. Remember that e is that irrational number that is approximately equal to 2.71. Whenever we say y is equal to e raised to the x, it's that same number, okay? All right, so anyway, to solve this differential equation, again, we realize that we have a second order linear homogeneous equation where all the coefficients are constants. So right away, we can go into our characteristic equation. And notice here that this is another one that can be factored out. So factored it out. We set each of these equal to 0, and we see that the result ends up being that r is either equal to -1/2 or a positive 3/2. So this is what our general solution would end up being just by basically sticking in the r1 and r2 in the exponents where you see them. Now, the more interesting thing here is using these initial conditions. Since I have what y of x would be in general, I can use this initial condition, but since I also have an initial condition that involves the first derivative, I'm going to have to take the first derivative of this particular function as well. So since this is one I've already worked out, I went ahead and just applied this first initial condition here by going ahead and plugging everything in. And of course, you see once I plugged in a -2 everywhere where I had x and made the entire equation equal e, then we see that just did some simplification here. So we end up with this first term here just having e raised to the 1, which is e in that first term. For the second term, that's going to be e raised to the -3 times the constant C2. And of course here, what's in common in what I saw here, there was what I could do to kind of make stuff even out here is I can multiply both sides by e raised to the -1. And I did that mainly so that I can get 1 here, okay? And of course, whatever the fallout is on the left side, it just is what it is. So this is one equation with two unknowns. We need another equation. And of course, we're going to get that from taking the derivative of this function here. So I'll go ahead and take the derivative of my general solution y of x, and then let x equal 2, let y equal to -e divided by 2. So you see that I do that here. And then to get rid of this fraction here, I decide to multiply both sides by a 2. Okay. So I do that. I get this result here. Then I say, hey, I really don't want the this e being here, or e raised to the 1 here. So I'm going to multiply by e raised to the -1 on both sides again. And of course, I get that. Now, if you look at what I have here and what I have up here, so look at these two equations here. Notice if I use the elimination method, C1 plus or minus C2 will cancel out, okay? And also 1 minus 1, if I add those together, that will cancel out. And so that makes it real easy to figure out what C2 is at that point, okay? So we do that, and we see after adding these two equations here and dividing both sides by everything except for C2, that ends up as a result, we see that C2 is just 0. And so after we know that C2 is 0, we plug this in, we see that C1 is 1. So what this ends up looking like here is, remember our general solution, C2 was 0. So all this goes away, and all we have left is whatever e raised to the -1/2 x is times the C1. And since this was 1, then that's how we get that solution of e raised to the -1/2 x. And that is what we got down here. All right, so next we're going to switch gears, and we are going to look at some case 2 examples. And so case 2 examples are the cases where our discriminant is going to be 0 for our characteristic equation. So when we do that, we know that we're going to, ideally, we would do reduction of order to figure out what is going to be our other corresponding solution to our differential equation. But of course, we already know what the answer is going to be, so we just use it, okay? All right, so for case 2, again, we have this second order linear homogeneous equation with all constant coefficients. We see that that ends up being our characteristic equation, which is just 2r minus 1 quantity squared. And we see that once we solve that quadratic equation, that r ends up being 1/2. So this is our general solution, and all we literally do is just plug in 1/2 there, okay? All right, so for second example, same thing. We look here, get our characteristic equation. Realize that this is going to be r plus 8 quantity squared. So r ends up being a -8. And literally all we have to do in this form here is just know what the form is, plug in r is -8, and we're done, okay? All right, so let's work this example together here. Again, we see we have a second order linear homogeneous equation with all the coefficients or constants. So we can go directly into the characteristic equation where A is 1, B is -8, and C is +16. So this ends up giving us r squared minus 8r plus 16 equals 0 as our characteristic equation. And if we factor that out, that is going to be r minus 4 times r minus 4 equals 0, or just r minus 4 quantity squared. Doesn't really matter here. Either way, it's going to be the same thing. If I set r minus 4 equal to 0, I'm just going to get that r is equal to 4. Okay. So because of that, my general solution is just going to be y of x is equal to c1 plus c2 times x. And this is going to be e raised to the rx, but of course my r here is going to be 4. Okay. So we'll go ahead and back that up. Yep. So this is just going to be 4x like that. And so that will be our general solution. Again, if you want, you can express this as c1 e raised to the 4x plus c2x e raised to the 4x. Expressing it that way is fine as well. So we have our general solution. Now we need to figure out what C1 and C2 are specifically, since we have these initial conditions here. Okay. So if we use the first initial condition, which is going to be y of 0 is equal to 3, then I'm basically going to take what I have here, and I'm going to use this form of it. So this will be C1 plus C2 times 0, all that times e raised to the 4 times 0. And then that equals 3. So if we work that out, this term ends up being 0. All this just ends up being 1. So I just have C1 times 1 equals 3. So of course that means that C1 is 3. Okay. Now, for the second initial condition, and that was y prime of 0 is equal to 14. The first thing I have to do is find out what the first derivative of my function y of x is. So I'm going to go ahead and do that now. So I'm going to use this first formula here, this first version of y of x here. So I'm going to take the derivative of the first. So derivative of any constant is 0. The derivative of c sub 2x is just c2. That derivative of the first times the second plus now first times derivative of the second, which is just 4e raised to the 4x. Now, we don't need to rewrite this y prime of x in a nice fancy way. So what we can do here is actually use what we have in this form to be able to get our second equation, or in this case, get our second coefficient C2. So here this means that y prime of 0 equals 14 is going to imply that 14 is equal to c sub 2 times e raised to the 4 times 0 plus c1, which is 3, because remember we found that out, plus c2 times 0 times 4e raised to the 4 times 0. Okay? And of course, on the left side, this just means we have 14. The e raised to the 4 times 0 is just 1. So this is just C2 plus, this is 0. That is 1. So we just have 3 times 4, really. So we got 3 in here. Got 4 out here, which of course that's 12. And this implies that C2 is just 14 minus 12, which is 2. Yeah. All right, so that's 2. So we got here C1 is equal to 3 and C2 is equal to 2. So now we have our particular solution is going to be y of x is equal to 3e raised to the 4x plus 2x e raised to the 4x. So that would be our final answer or final solution for this differential equation. All right, so for our next example here, our characteristic equation, again, is just going to be 4r squared plus 4r plus 1 equals 0. And we know to do this, again, because we have a second order linear homogeneous equation where all of the coefficients are constants, okay? Now, if we do this, this turns out to be 2r plus 1 times 2r plus 1 equals 0, which essentially means here that 2r plus 1 is equal to 0, which essentially means that r is equal to a negative 1/2 once we solve for r. So we see because we have the double root here, I know I haven't been writing this out before for the case 2s, but because we have the double root, this is what lets us know that our solution, our general solution for this differential equation is going to look like this. And of course, all we have to do really is just plug in the r is equal to negative 1/2. So this just ends up being C1 plus C2x times e raised to the negative 1/2 x. Okay. So now that we have that general solution here, of course, we have our initial conditions. So that means we could find C1 and C2. This time I'm going to go ahead and elect to take the first derivative of this before we start using the initial conditions. So using it in this form here, the derivative of C1 plus C2x, because I'm going to use the product rule here. So I'm going to do derivative of first. That's just going to be C2 times the second function plus first function times derivative of the second function. And this would be a minus 1/2 e to the minus 1/2 x via the chain rule. So now that we know what our first derivative is, we're going to go ahead and apply these initial conditions. So the first initial condition is going to be y of 0 is 0. So here we're going to use this first differential equation here. This first solution to this differential equation. And so this means that I'll have C1 plus C2 times 0. And all that is equal to, all that's times e raised to the negative 1/2 times 0. And that is equal to 0. Yeah, that's what I was trying to get to. So if we do all that, of course, this second term here is 0. All of this is just 1. So what we end up with is C1 plus 0, which is just C1, that equaling 0. So we know what C1 is now. So now using the other initial condition, y prime of 0 is equal to 1. We see here we have y prime here. So all I need to do is substitute in 0 for x and 0 for C2 actually. All right, so sorry, 0 for C1. So here we have C2 times e raised to the negative 1/2 0 plus. Now here we have 0 plus C2 times 0. And I guess it really doesn't matter what all this other business is because it's all going to be 0 here. And all of this is going to equal 1. So here we know all that goes to 1. So this is just C2 plus. Since all this is 0, 0 times anything is 0. So we have that. And this tells us that C2 is 1. So now that we have what C1 and C2 are, we go back to our original general solution here. And we see that C1 is 0. So this is just going to be a function of whatever C2 is times x e raised to the rx. So our final answer here would be y of x is equal to x e raised to the negative 1/2 x here. And of course, we know since C2 is 1, a 1 would be right here next to the x. 1 times x is x. So that's why I didn't write a number there. And remember that our root for our characteristic equation is going to be minus 1/2. So that's why we have the minus 1/2 up here in the exponent. All right, so we're finally going to get into our case 3 examples. And so these will be the examples to where our characteristic equation will produce complex conjugate solutions. And thus we'll have to use the case 3 form of a general solution for this type of ODE, where it's just e raised to the lambda x times the sum of sine and cosine functions. Okay, so we can see from here that this is a second order linear ODE again. This is where A is. This is where B is. And of course, since we don't have, this is where C is. So let me change that right quick. Yeah. This is where C is. Notice that we don't have a y prime term. So that's 0 times y prime. So our A is 1, our B is 0, and our C is 36. Okay. And so that's how we end up getting this r squared plus 36. And of course, if we subtract 36 to both sides and then take the principal root, we see that we end up having the complex numbers plus or minus 6i. And then, of course, since these are imaginary conjugate numbers or complex conjugate numbers, we could translate this as 0 plus or minus 6i. Now, this is what it is as pure imaginary, but here I've translated it into a complex number so that we can make sure that we have both a lambda and an omega, meaning the real part of our complex number and imaginary part of our complex number being explicitly shown. So here's our general solution. I know where I have lambda, I just need to put a 0. Where I have omega, I just need to put 6. And so that's basically what I need to do here. So I plug in everything and I see that C1 cosine of 6x plus C2 sine of 6x is going to be my general solution for this. And of course, this when lambda was 0, e raised to the 0 times x is just equal to 1. So that is why this ends up not having a e raised to the rx part, or e raised to the lambda x part. Okay, so our next example of a case 3 type of second order linear homogeneous equation, we'll have the main difference here is that whenever we get our roots from our characteristic equation, we're going to have both a real and an imaginary part to it. So it's going to make our final general solution look a little different. So of course here we see that our Coefficients here are going to be 1, minus 4, and positive 13 respectively. So that turns into our characteristic equation of just 1r squared minus 4r plus 13. And for here, we won't be able to factor this one out, nice and easy. So quadratic formula is kind of the way to go for this one. And of course, our quadratic formula, we're just plugging in our b here, same b there. This is a, and that is c, and of course, that's a there. So we go ahead and do all that, do all the work for it, and we see that we end up with 2 plus or minus 3i. And so we let 2 end up being our lambda and 3 being our omega. And this should say plus or minus. So, of course, the 3, which is the coefficient for the imaginary part, goes here. And the 2, which is the lambda or the real part, goes here. And so we see that we have e raised to the 2x times c1 times cosine of 3x plus c2 sine of 3x as our final answer. All right, so let's move into some examples here where we'll have some initial conditions. All right, so for this example, we see that we pretty much have the same problem that we had last time, but now we have these two initial conditions with it. So what we're going to do is copy down the general solution from the previous problem. So I'm just going to copy that down. And so now what we need to do is, of course, apply this initial condition to the current equation that we have here, but we also need to find the first derivative so that we can apply this initial condition as well. So I'm going to go ahead and find the first derivative for this before we apply the initial conditions. So here we can use the product rule again. So I'm going to take the derivative of the first function here, which would just be 2e raised to the 2x times all this business here for the second function. And then we'll add, and then it'll be the first times the derivative of the second. And of course, we know that we will have to end up using the chain rule here. So the derivative of cosine of 3x will be a minus 3 sine of x. So this will give us a minus 3 c1 sine of 3x for the derivative of the first term. For the second term, ignore the constant. The derivative of sine 3x is just 3 cosine x. So this will be 3 c2 cosine of 3x. Okay. And again, there's no need for us to try to combine like terms and all that in this sense, because we're really just using the derivative here so that we can figure out what c1 and c2 are. So now that we have all that done, we'll apply the first initial condition, and this one will be y of 0 is equal to 1. So everywhere where we see x, put a 0. And of course, y of x here total is going to equal 1. So this would be, I'm going to go from left to right here. So this will be 1 is equal to e raised to the 2 times 0, c1 cosine of 3 times 0, which is 0, plus c2 sine of 3 times 0, which is 0. Okay, and I could have did the same thing here, but I didn't. So cosine of 0 is equal to 1, sine of 0 is 0. So all this just ends up being that 1 is now equal to 1 times over here c1 plus 0. So that's c1 So C1 just ends up being 1. For our second initial condition, again, going to say y prime of course, put in a 0 there. All that's going to equal 0. And again, the same thing. 2e raised to the 2 times 0 is 0. My C1 here is 1. So I'm just going to do 1 times. Cosine of 3 times 0 is 0. Plus C2 sine of 3 times 0 is 0. And then plus e raised to the 2 times 0 is 0. And then we have minus 3 times 1, because C1 is 1. Sine of 3 times 0 is 0. Plus 3C2 cosine of 3 times 0 is 0. And close that off. All right, so cosine of 0 is 1. E raised to the 0 is 1. Sine of 0 is 0. So that means all this is 0. E raised to the 0 is 1. Sine of 0 is 0. So that means all of this is 0. Cosine of 0 is 1. So now we have 0 is equal to 2 times. Inside of here we have just 1 plus 0, so that's 1 there, plus 1 times. We have 0 plus 3C2, so that's just going to be 3C2. And that's it. So what this means here is that we just have 0 is equal to 2 plus 3C2, which means that we have minus 2 is equal to 3C2. And finally, this just means that a minus 2/3 is equal to C2. And now that we know that our particular solution here is going to be y of x, e raised to the 2x, times C1 is 1, so that'll just be cosine of 3x, plus C2 is a minus 2/3 here, so we will put in a minus 2/3 sine of 3x. And that will be our final answer for this particular problem. Okay, so I have one more final example here, another initial condition problem. As you can see, though, the initial conditions here look a little bit more interesting than what we've had before. So I wanted to at least go through an example like this one, which you're dealing with some numbers that are a little bit more complicated. But again, the principle is the same. So we start off here by our characteristic equation. Our characteristic equation here will just be r squared plus r plus 3.25, and that will equal 0. And of course here I not going to be able to factor that out real easy, so I'm going to just use the quadratic formula to figure out what my solutions will be. So this is going to be, of course, minus b plus or minus square root of b squared minus 4ac all over 2a. And our b here, so let's just list this out. So our a is 1, our b is 1, and our c is 3.25. So I have 1 here, plus or minus 1 squared minus 4 times 1 times 3.25. And all that over 2 times 1. So from here, of course, we have a minus 1 plus or minus. This will be square root of 1 minus, and 4 times 3.25, that'll end up being 13. All that over 2. And this is going to be a minus 1 plus or minus, we'll say I times square root of 12 over 2, because 1 minus 13 is a negative 12. And of course, we could rewrite square root of negative 12 is just I times square root of 12. I'm going to come back up here. So therefore, we know square root of 12, we can just rewrite square root of 12 as square root of 4 times square root of 3, and square root of 4 is 2. So here we're going to rewrite this as negative 1 plus or minus 2 times square root of 3 I, all that over 2. Okay. And to have some separation here, just going to rewrite it like this. And so I'm doing it this way so that we can have a distinct lambda and omega. So this implies here that our lambda is going to be a minus 1/2. And our omega or w here is going to be square root of 3. So now that we have that, we know what our general solution is. So our general solution for this case is going to be e raised to the lambda x times c1 cosine of omega x plus c2 sine of omega x. That x did not come out real pretty. All right. And thus, this means here that we have e raised to the minus 1/2 x times c1 cosine of square root of 3x plus c2 sine of square root of 3x. So that is our general solution. So we now have two initial conditions. Let's go back up to the top here. So this is our first initial condition. This is our second. Again, we're going to need the first derivative to be able to find one of the coefficients here. So we're going to have to need to take the first derivative, and I'm going to go ahead and tackle that now. Okay. So we know that this is our original solution here, and we're going to go ahead and figure out what our first derivative of our general solution is. So we take the derivative. So we take the derivative of the first, which is just minus 1/2 e raised to the minus 1/2 x times all of this business here. Plus, and now we just have e raised to the negative 1/2 x times, now we take the derivative of each term here. So we take the derivative of cosine of square root of 3x, that's just going to be a minus square root of 3 sine of 3x. And of course, we also have that constant c1 there, so have to include that. And notice that this x here is not under the square root sign, okay? Take the derivative of the second term. This will be square root of 3 times c2 cosine of square root of 3x. And again, just like in the other problems, it is not important for us to try to simplify what the first derivative is down into simplest terms, because we're just using it here to figure out what our constants are. So no need to do any simplification. It actually makes it harder when you do that. All right, so for our first initial condition, which we said this was y of pi over square root of 3, and that equals a -2. We're going to plug all this information into our original or our general solution for our differential equation here. So what this is going to mean on the left just equals -2. All right, I'm going to scroll up some here. So on the right side, this is going to be e raised to the 1/2 times pi over square root of 3. Okay. And then here on the inside, this is just C1 cosine of square root of 3 times pi divided by square root of 3 plus C2 sine of square root of 3 times pi over square root of 3. Okay. So from here, we know that square root of 3 and square root of 3 reduce to 1. So this will reduce to 1 here. This will reduce to 1 here. And so now what you see is that we have cosine of pi. Okay. And if you remember, cosine of pi is going to be a -1. And sine of pi is going to be 0. So this cosine of pi here, all of this is just going to be 1. And all of this is just going to be 0. So when I do that, what I have over here is just e raised to the -pi divided by 2 times square root of 3. And I'm just going to leave it that way for now. And over here, I just have C1 plus 0. So that's just C1 here. And so this implies that C1 is just going to be a -2 divided by e raised to the minus pi divided by 2 times square root of 3. Yep, so not the prettiest looking thing, but that is what it is. I'm going to clean this up a bit by rationalizing the denominator. It's not necessary to do it, but I'm going to do it just because it's going to make it look a little bit cleaner. So here, this will be a -2 over, and if I rationalize the denominator, I'm going to do it up here. So I'll rationalize the denominator here. Of course, I have a minus there. That is just going to be a -square root of 3 pi all over 2 times square root of 3 times square root of 3, which that's going to be 6, because square root of 3 times square root of 3 is 3, and 3 times 2 is 6. So we have that. So this will be e raised to the -square root of 3 here, pi all over 6. And we could put this up in the numerator, and this will just be all that over 6. Okay, where this square root of 3 times pi divided by 6, all that is in the exponent. So that's a way that we could actually handle that. And I'm just trying to make sure I didn't miss any signs here. I may have, let's see. Yeah, I'm just trying to double check the work just to make sure I got everything here. Oh, yeah, I did miss a sign. So here, cosine of pi is -1. Yep. So that means this is going to be this times -1 here, which means that should be negative, which means this should be positive here. So that should be positive. Yep. Okay. Yeah, because I knew something didn't look right. All right, so we know what C1 is now. So I'm just going to write it here, make it try to look nice. So that is C1. All right, so now we need to do our second initial condition. This is y1 prime of pi divided by square root of 3. And that one was equal to 6. And so now we're going to use this first derivative here. Of course, it's really long, but actually keeping it this way will actually make it better to evaluate in the long run. So we know that y prime, whenever we plug in x to be pi divided by square root of 3, it's going to be equal to 6. So we're just going to say 6 is equal to, and then this will be 1/2 e raised to the -1/2 times, and of course, pi divided by square root of 3 again up here. All that times C1 cosine of square root of 3 pi over square root of 3 plus C2 sine of square root of 3 times pi over square root of 3. All that plus e raised to the -1/2 pi over square root of 3 here. Now we have a minus square root of 3. I'm going to wait to put in C1 until later, after we do some simplification here. Sine of square root of, that didn't turn out too hot. One more time. Yep. All right, so this will be square root of 3 times pi over square root of 3. And then we have plus square root of 3 C2 cosine of square root of 3 times pi over square root of 3. Okay. So now we got that all in there. Let's do simplification like how we did last time. So here we know that square root of 3 and square root of 3 here will reduce to 1. Square root of 3 here reduced to 1. Square root of 3 here reduced to 1. Square root of 3 here reduced to 1. We also know here that cosine of pi, all this is going to be a -1. Sine of pi, all this is going to be 0, so that means this whole term goes to 0. Same deal here, sine of pi is 0, so that means this whole term goes to 0. And here, cosine of pi is going to be -1 here. Okay, and we'll get rid of these just so that we don't confuse ourselves later. Okay, so now that we have all of that, this implies that 6 is equal to -1/2 e raised to the, and I'm going to go ahead and rewrite this as is square root of 3 times pi over 6 deal. So this will be minus square root of 3 pi all that divided by 6. And this will be a minus C1 plus 0. Again, e raised to the minus square root of 3 pi, all that divided by 6. And so we got 0 plus square root of 3 C2. And because I have the minus 1 here, this term here should be negative. So I'm going to go ahead and change that. Okay. All right, so we're getting a little closer. And so here, I think I'll just go ahead and skip down to the next page. All right, so we just skip down to the next page here. And so therefore, I'll have 6 1/2 e raised to the minus square root of 3 pi over 6. And this minus and that minus there work together just to be a plus. And C1, if you remember, we go back up here, C1 was 2 times e raised to the square root of 3 pi divided by 6. So this would be 2 times e raised to the square root of 3 pi divided by 6. This will be plus e raised to the negative square root of 3 pi divided by 6. And this will be minus square root of 3 C2. Now, for this first term, what we see here is that this 2 and this 2 will reduce to 1. And when I multiply this term and this term together, I'm going to have a net result of e raised to the 0, which is also 1. Okay, so this whole entire term here is just going to turn into 1. Okay, very convenient for us. So we're going to go ahead and write that. So this is going to be 6 equals 1 plus, and of course we have all this other business here. Negative square root of 3 C2. And this is e raised to the negative square root of 3 pi divided by 6. And so now we're pretty much just solving for C2 at this point. So first thing that we want to do is subtract 1 from both sides. And so we'll get 5. Next thing that we want to do is divide both sides by everything other than C2. So this will be 5 divided by negative square root of 3 e raised to the negative square root of 3 pi divided by 6. And here we can just have 5 divided by negative square root of 3. And we can move this e raised to the negative square root of 3 pi divided by 6 up to the numerator. And so with that, we finally have our value for C2. It's not pretty, but it is a value. And so now that we're done with all that, we can go ahead and put together what our final answer is going to be. Okay. So this is our C2. We go back here. This is what our C1 was. And this was what our original solution is going to be. So we need to put that all together. And like I said, if you want to keep track of all this, you may want to pause the video, write that down, and then put everything together towards the end. All right, so when we do all of that, what we're going to see we end up getting for our final answer here is going to be e raised to the negative 1/2 x, all that times 2e raised to the square root of 3 times pi over 6 in the exponent times cosine of square root of 3x. And then this will be minus 5 times square root of 3 sine of square root of 3x. And so this is our final answer. And so with that, this concludes the video on solving second order linear homogeneous equations where all of your coefficients are constant. I hope this video helped. Take care.